All right, everybody's got to keep it clean now. Homework due Monday. Remember the Hailstone sequence.
So we don't have to write out the actual sequence for the users.
You don't want us
If they want it.
Like this.
Oh, that. No.
Yeah.
This program computes the Hailstone sequence. Enter a starting term. Yes. Yes. No.
Is there a way to link it to like something to a Wikipedia file within a code?
I mean, you could print out a URL if you wanted or something like that, but no, we're stuck with text terminals and things like that.
Well, if like you wanted to do the above and beyond, for example.
Right.
Could you link it your code to like the Wikipedia site to explain it? So.
Not in any kind of simple way. You can. There's something called the system command in C, C++, where you can actually send a command to the operating system, and then you could sort of send a command. You could run a browser with a particular link in it or something like that. But I don't want you guys messing around with the system command at the moment. All right. So today, my hope is to let's see. We're going to continue talking about generating sequences with loops. I'll finish talking about the loop that I started last time with Fibonacci sequence. We kind of ran out of time at the end there, and I wanted to make it perfect, so we'll talk a little bit about that. I want to do a brief aside to a favorite website of mine called the Online Encyclopedia of Integer Sequences. And then perhaps at that point, Chris will do his thing. And then I will continue and introduce a new kind of loop called a for loop. And we'll talk about how for loops and while loops, you can pretty much always do what you can do with a while loop, you can do with a for loop, and vice versa. So there's nothing, there's no sort of new features that you're getting with the for loop that you didn't already have with the while loop. It's just a different way of looping in C and C++. Any questions before I get started? Oh, and then what I'm going to do is finish off with a discussion of homework 3, three important details. Number one, how are you going to generate the terms of the sequence? How will you decide to show the terms or not? And how will you count the number of terms? I'm leaving this to the end because I've learned over the last couple of semesters teaching this class that there are some people that don't want to hear discussions like that. They want to go and figure it out themselves, and that's great. But if you want to stick around, so when I get to that point, I'll say, if you don't want to hear about this, hit the road. And then the people that stay behind will talk about hints, strategies for accomplishing each of these 3 important tasks in your program. Questions? Great. All right, first things first, generating sequences with while loops. I want to return to the Fibonacci sequence that we started at the end of last period. And if you'll remember, I think it wasn't quite behaving the way we want. So I ask for, say, 5 terms, and what I get is too many terms. 1, 1, 2, 3, 5, 8, 13. That's 1, 2, 3, 4, 5, 6, 7. So what I want to do is make this really precise. I want to make it so that it prints out precisely the number of terms that I'm asking for. So let's go back in and look at the loop that's generating this stuff. Also, I wanted to fix this little guy here. That's not quite what I want. Well, yeah, let's just do it that way. So let's see. If I want 1 term, I want to do that. If I want 0 terms, I want nothing, so I don't need to do anything there. And if I have more than that, I think that'll work. So what happens if, just back to fixing the beginning here, if the person responds, is the respondent is sort of curmudgeonly and says, I want to see 0 terms, I start out with the count equals 0 and number of terms equal to 0, and then the person just puts in 0 number of terms. Is this going to happen? No. What about this? What will happen here? The while loop.
Count will equal some terms, so it won't go into it.
Right. And so you'll see nothing. All right. Well, still not sure I've solved the problem yet, but let's just see how it's behaving right now. So let's say I want to see no terms. That's good. Let's say I want to see 1 term. Not so good.
Subtract from your count because you put 1 for the first term, but that's not included. That should be included in your count, but in your program it's not included.
Right. So how to fix?
Count plus plus after the.
Very good. So that makes logical sense, right? If I'm being really careful, count is keeping track of how many terms I have. That works, right? All right, let's see if we get better behavior now. Okay, good. All right, let's see how things work if I do 2. Well, that's not quite right.
Change it. You change the number of terms. The if, or say if it's equal to 1, but you want to say if it's equal or greater.
Okay, let's do that. So I would still like to see, let's do 1 term. Good, let's do 0 terms. Good, how about 2 terms? Still not quite right. It's supposed to be 1, 1. Ideas?
Add another interest line at top for greater than or equal to 2.
That could work. So now I could change this back to equals, I suppose.
No, because you want
Oh no.
to count.
Yes, thank you. Oh my. Zero, 1, 2, 3. Ten. Oops. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All looks good there. And this will go pretty far for you. You could do 100. Can't go quite that far. What happened with 100? So somewhere right around here, right? How do I know that there's a problem? Should never be a negative number in the Fibonacci sequence, right? This is clearly a positive integer sequence. So once I get here, I know I have a problem. And frankly, prior to getting there, I'm okay. I think I'm okay. I guess we should be careful about that. We're not really sure if we're okay, because you could wrap around, and you could wrap around so far that you actually land back in the positive territory again, right? So you do have to be careful. It takes a little bit of thought. to figure that out. So what you really have to do is make sure that the numbers leading up to this first minus sign are less than that max integer that we explored in the last homework. Okay, so what we could do is, let's see here. If n is greater than max int, break. Int max maybe? I can't remember. It's been a while since I used this one. Yeah, I think that's it. Maybe it's in C standard def. C standard def. Nope. Maybe max int is in C standard def. Although this one highlighted, didn't it? Mm-hmm. And the other one didn't. I'll look it up. It's been, like I said, it's been a while. Limits. Okay, so C limits. And am I using ints here? Yes, I am. Yay. So now I'll try 50. Nope. Still not quite there. Yeah, that's not the right way to do it either. Because it gets, once it overflows, it wraps around, becomes negative, it's still less than max int. I don't know, I'll think about that one. Anyway, you could put in some kind of check to abort the loop when, yeah.
Can you say if n is negative?
Well, it doesn't get me to that issue that I was talking about before where what I could do is use an unsigned int. And then, still doesn't quite get me there. Oh, you know what you could do? So you could take the current value and figure out what you're going to add to it to get to the next one. And if what you're going to add to it goes past max int, then quit. That's what you could do. We're not going to do that, but that's what you could do. Okay, let's move on then to, I think I've beat this example into the ground. Let me get rid of this guy so that we have something that actually works. All right, yeah, go ahead.
If you use unsigned int, would it allow you to go higher?
Yes.
Okay.
Yes. So I can make a note of that here. Unsigned int is as big as it gets, I think. Don't hold me to that, but I think that's the case. If you really want to go past that, then there are actually special libraries that let you handle giant integers that you have to import from external sources. These are really common issues. For example, something that we haven't had a chance, in fact, here's a nice example of a loop and a segue into an interesting discussion. Let's look at a program called machine epsilon. And it's been a while since I've done this one, but I think I can remember how to do it. Somebody knows this one? So I'm going to give myself a double. I'll call it E. And I'm going to set it equal to 1. And let's see, while 1 plus E is greater than 1, we're going to do the following. We're going to let E equal E over 2. And we're also going to print out Let me just stare at that for a minute and see if it does what I want. What do you think is going to happen when I run this?
Converge towards 1.
Every time I go through, I take E and I overwrite it with half E. So the first time through, it starts out E as 1. Is 2 greater than 1? Sure. So now E becomes 1/2. I print out a 1/2. I come back up here and I have 1 plus 1/2, which is 3/2. Is that bigger than 1? Sure. Now I come in here and it turns into 1/4, and I keep going. What do you think is going to happen if I run this program? Is it an endless loop?
Well, is there going to be a degree that it can't express the values? Right?
Yeah, that's what's. It looks like an endless loop. On the face of it, it looks like, because no matter how small E gets, 1 plus E is going to be bigger than 1. But that's the mathematical, abstract reasoning. That's not what happens in a computer. All right, let's look at where this thing starts. It starts in familiar territory. But as I keep dividing by 2, I start having to use scientific notation to express the values. And as I keep doing it, that scientific notation goes all the way down to something like 1 times 10 to the negative 16. What this is telling me is, at best, your C++ program using double precision variables can accommodate 16 digits of precision. Once you get past that, sorry, you can't distinguish between, data that's more than 16 digits, 16 decimal digits of precision apart. So essentially what we're trying to do is compare 1, right? 1 just sits there constantly 1, and then E gets smaller and smaller and smaller. So it starts out 1.5, 1.25, but notice zeros start to creep in. So the 1 is still sitting out here, 1 plus E. The 1 is still sitting out there, but zeros start to separate, start to push the significant digits apart. So you have this 1 significant digit all the way at the left, and then the rest of the significant digits are getting pushed away. The width of significant digits on this machine is about 16. That's how far apart significant digits can be on this machine. And that's something called machine epsilon. This little E here is machine epsilon. This is a vast area of study in both upper level undergraduate classes and graduate level classes. Something called numerical analysis really explores these issues very deeply. Taking a mathematical problem which on paper with your pencil is exact, and putting it into a computer changes those problems, often changes those problems. And so this piece of code, which on the face of it looks like it should run forever, doesn't. And these are really important issues for computer scientists and mathematicians alike. Machine epsilon, that's that guy. So we've got Fibonacci, we've got machine epsilon. Loops are really great tools for generating sequences. Let's do a couple more examples. Let's do one that generates bless you. Let's do a loop that generates the first n positive odd integers. So I'll do the first part for you. So I asked the person, how many odd numbers do you want? I'm being very brief here, but I'm talking about positive odd numbers. 1, 3, 5, 7, 9, etc. Let's see if we can't write a loop that will generate 1, 3, 5, 7, 9, etc. Up to however many the person wants. Say it again? Oh, yes. Thank you. So if I want to generate odd numbers, and I want to generate capital N of them, I think a good place to start would be to develop a loop or design a loop that runs precisely n times. And then figure out what to put in the loop to make this happen. So can you describe for me a while loop that will run precisely capital N times? Okay, so I better I have to define I. And one more thing I have to do. I have to initialize it. Is 0 the right thing to do to make it run n times? So how do you decide whether it should be 0 or 1? Do a little thought experiment. Pretend that n is 1. Pretend that n is 1. So now instead of having n here, you have a 1 sitting here. And you come along and you say, is 0 less than 1? Less than or equal to 1? And you say yes, so run the loop. Now we get back up here, what's I? Is 1 less than or equal to 1? Yes, so it runs again. Now we get back up there and what? It's 2. Is 2 less than or equal to 1? No. So we've gone one too far here, and the people that were suggesting that we should do this at 1 are correct.
Couldn't you also say, make it equal to 0, but take away the equal sign?
Absolutely. And that's something that I can't emphasize enough. There are always a half a dozen different ways to write the same loop. Here's one. So we now have a loop that will run n times. What we need now is a formula to generate odd numbers. And it would be really convenient to just use I somehow to generate those odd numbers. Some formula that involves I that will generate 1, 3, 5, 7, 9. Go ahead.
I equals 2i plus 4.
So I don't want to do this. Right, because I don't want to change I. I've already taken care of changing I the right way. And if I do this, what I'm going to start doing is changing I. But you're on the right track. I want to print that guy out. Think about what this is going to do. It comes in, and I is equal to 1. And what prints out? 3. Not quite right, but you get the idea. I go around, I becomes 2. What prints out? 5. So it's 3, 5, 7, 9, etc. Of course, we want it to start at 1. Is there a way to fix that? Change what to a minus 1?
2 times I, make that minus 1.
That'll fix it. And again, half a dozen at least different ways to do this, because if we use racial suggestion, we start at 0, make this strictly less than, then we could have used 2i plus 1, right? So it's really just a matter of what's your loop doing, what are the values that you're cycling through, and make it work for your loop. There's no kind of general approach, and there's no one single right answer for one of these loops. Well, let's do the thought experiment again. I is equal to 1. The first time through, 2i minus 1. 2 minus 1 is 1. 3, 5, 7, 9. This loop runs precisely n times, so this ought to give us the first n odd integers. If I want to make sure and just kind of label it, I could do something like just print out I and a colon perhaps. And this will actually count the number of odd integers. So 1, 3, 5, 7, 9. The loop ran precisely 5 times. The loop started with the first odd integer and ended with 5 odd integers. Questions about that? What if I wanted the first n even?
Get rid of -1.
I could get rid of the -1, and it depends on what we're talking about. But the first positive n, the first n positive even integers, this would certainly work. So there's the first 5 positive even numbers. Formulas for odd and even are good to know. So 2i plus 1, 2i minus 1 gives you odd numbers. 2i gives you even numbers. Questions about that? So this leads me to the last thing before I let Chris go. This is a really remarkable site. Started many years ago. One of the oldest sites on the internet, actually, and it hasn't changed very much over the years, except the content that's been added to it has changed quite a lot. Why is this a really useful site? Well, let me plug in a couple of. Let's do 1, 1, 2, 3. 5, 8, 13, and click search. So this is an aside. This has nothing to do with programming at the moment. It goes through some kind of search algorithm, and it comes back with this statement that, oh, these are the Fibonacci numbers, and here's lots of information about these Fibonacci numbers. Let me throw another one in there and see if you can recognize it. 1, 1, 2, 6, 24, 120. Does anybody know that one?
So it's 1 times 2 times 3 times 4 times 5.
Ish. You're getting there. You're exactly right. What's that called? Factorial. Yeah, so those are the factorial numbers. 0 factorial by definition is 1. 1 factorial by definition is 1. 2 factorial, 2 times 1 is 2. 3 factorial, 3 times 2 times 1 is 6. 4 factorial, 4 times 3 times 2 times 1 is 24. 5, etc., etc. These numbers grow really quickly, as you can see below.
How many are in their database?
How many different sequences? I have no clue. Many. Let's see here. How about this one? 10, 5, 16, 8, 4, 2, 1. Let's see what it has to say about that. Well, it has some words at least that we recognize. It's got Collatz in there. Remember I said that the Collatz conjecture is about the Hailstone sequence. But you can keep reading down and see lots of different references. There is an actual formula for the Hailstone sequence. A1 is equal to 1, AN equals this, if AN minus 1 is even, AN equals that otherwise. So there's the definition of the Hailstone sequence that you're using. And all kinds of just related stuff. Okay, how about this next sequence? Nobody's going to get this one. Five, 9, 14, 27, 29, 54, 59. Ideas?
Add the previous number.
Works for the first, for 14. Give up? Major League home run records. How many home runs did you hit that? How many home runs were in the Major League home run record until it was broken? So 59, 60, 61, 70, 73. Anyway, lots of sequences hiding in this thing. What is this really useful for? What this is useful for is if I'm a mathematician or a computer scientist and I'm working on some new area of mathematics or computer science, and I notice that I'm getting this particular sequence of numbers and I don't know why. I can punch that sequence of numbers into this thing and I will get a long list of references of different mathematical ideas that are related to this sequence. And one of those ideas might actually help me in my research. So this is a fantastically useful website for mathematicians that are researching, who are doing research of any kind that generates sequences of integers. Okay, let's pause there, let Chris do his thing, and then I'll pick up and finish with for loops. Do you need the computer, Chris?
Yeah.
Okay. Let me know when you're ready. I'll mute the screen. What's your question? Chris, what was your question?
I had a question.
What are you talking about?
Oh, Java.
Sorry?
Java.
Java. Okay, so a different programming language than C++. Java, pretty popular, although seems to be slightly waning in popularity in recent years, but has some interesting commonality and differences with C++. You ready?
Almost. Yeah, right, go ahead. I'm just loading up my email here.
See, now I'm showing you I'm showing everybody your mailbox.
Awkward.
Okay.
All right, so this guy is to Java what the man we heard of on Monday is to C++. He was working for Sun Microsystems around 1991. He and a team of guys were looking for figuring out a new language to fit the new computing era that they saw coming. And they're specifically focused on consumer devices and web development. So their goals for Java were to have it completely object-oriented, built from the ground up as an object-oriented system. Now, you may remember from Monday that that was also one of the things that was built into C++, but unlike C++, this doesn't have any of the non-object-oriented structures except for variables, basic numbers, and Boolean values. So I'm just going to bring up the basic Hello World program here so you can see what that looks like in Java as compared to what we're used to. So as you can see, instead of having our main function, we create a class, Hello World, and then within that class, we have an object, or string object, and then we print out Hello World. So that's how that works. Let's see. One of the other main things about Java that's different from C++ is that it has garbage collection. In C++, when you are using resources, let's say you define an array or some data structure. You need to allocate memory to use for that, and then later on in the program, you need to say that you're not using this data anymore and to clear up the memory. If you don't do that, then you have what's called a memory leak, where your program still has this area in memory that's allocated for whatever task it is that you're using it for, and using up your memory for no real reason. So what the Java developers did is they created an automatic garbage collection. It just when you're done using an object, a data structure, it'll just make that memory available to the computer again. So it's intended to be a more user-friendly programming language. Let's see, some other advantages of Java are user-friendly build tools. It doesn't have pointers, which helps for not accessing points in memory arbitrarily. Some other basic things that we don't really know about yet. And portability is is a big thing about Java that has over C++. When you compile code in Java, it doesn't just go straight to, it's not a straight translation between what you write here and the machine code. There's an intermediate step. And I have another picture for that, so let me bring that up. Oh, wait. You take your code, and the compiler turns it into Java bytecode. And then the bytecode is translated, it works on the Java virtual machine. It's called the Java runtime environment. You may have seen it on your desktop or needing updates or what have you. So on all computers that have Java, you have this Java virtual machine, the runtime. You install that at some point, and that's specific to your system. And then, so all the Java code, all the bytecode needs to do is talk to this virtual machine. It's like you have, instead of having a different computer for every computer, you have the same virtual computer on all computers. So you don't need to recompile every time. You just speak to that virtual machine. So it's a very portable language. And that's a good thing. And the last thing I want to show you is some more complicated code. I'm not really going to get much into this, but I just want you to kind of see a little bit about this. You can see, for one thing, that in the top area of the code here, there's just I would assume, because Java is built ground up as object-oriented. Using object-oriented code is more straightforward. You can see there's less there. And you may be wondering why we don't use Java, or maybe you're not wondering, but in any case, the only thing that C++ does better than Java is the very lightweight programs, because you don't need to have objects all the time. You can just do the simple code we use for most of our programs. Just putting in the loops and sequences and whatnot without declaring objects. You can have very lightweight programs that start up quickly and that execute quickly. So quicker startup and less memory use for smaller programs. And that's all I've got. Do you have any questions?
We have to have be able to find a web page with a Java application on it, would you?
Let's see. I mean, Java applets are used not uncommonly.
I have one. So I just want to demonstrate sort of what he was talking about with let's go here and here and this is one of the programs I use to teach myself to how to write in Java. just go. Yeah, okay, so this is a Java application, and what's useful about Java is I can write this program once, and then I can hit it with my Windows machine, and you can hit it with your Mac, and somebody else can hit it with their Linux machine, and all three of them will be able to run it without recompiling. That's the virtual machine idea. And so this is one of the early languages that was expressly designed for the use on the web. Because if you're on the web, the website doesn't know what kind of computer you have. So they need some way of sending a program to you that'll work on your computer. This is slowly being superseded by something called JavaScript, which is a language that's built into almost all modern browsers. But Java is still out there and still widely used, and it's also heavily used in embedded devices.
Oh, and I was going to mention it's built to be very similar to C code. So in terms of syntax, in the code you can see there's it's very similar.
Yeah, you can see, for example, lots of semicolons. Yeah, all the file operators are the same, plus, minus. There's an assignment operator. Everything's basically C syntax, in a sense. So C++ didn't make it up. It was Dennis Ritchie with C that really started all this syntax. And frankly, he probably got it from somebody else. So, okay. Alrighty, let me quickly show you a for loop. In fact, let me save this guy, and we'll redo this guy as a for loop. Alright, so the for loop is a wildly different kind of syntax. The main reason for the for loop syntax is if you want to go through a particular block of code a particular number of times, like this while loop is doing, if it's a really large, complicated loop, you have three very important moving parts here that control how many times this loop runs. You have the condition, you have the increment, and you have the initialization. What the for loop does is puts all three of those extremely important pieces of information for the loop in one place. Alright, so what I've just done is replace the old while loop, which if you want to see it again, you can go look at the other file. I've replaced the other while loop with the equivalent for loop. Let's see that, in fact, it does still do exactly the same thing. Oh, still doing the even stuff here. And still not sure why I'm only getting 3 terms there. Oh yes, thank you. Right after I said all those things have to be in the same place. Okay, so now we're back to doing the same thing. All right, let's talk about how the for loop works. Might be useful if I could somehow, let's try something here. And then let's go here. Yeah. Don't know if I can blow it up at all. Probably not. Do you get tired of watching me play with this? I hope that was exciting. I don't even know what that is. This is my Windows 8. I have no idea how to use it. How about escape? Okay, I'll just go over here and do that and that. Okay. I wish this could be bigger. Can I make this bigger?
You can make the text bigger.
Yeah, that's what I want to do.
Home.
Okay.
Yeah, and then.
There we go. Good call. There we go. Lovely. Thanks again, Emily. Do you really?
Yeah, I like it.
I do too, actually. Okay, let's talk about for loop. So this bit right here. Let me get my pen out now. Hope that it actually works. This bit right here is the initialization. And it only happens once. Okay, and then after that happens, it will go here to this bit. And this is the condition. If that condition is true, then run the loop. Otherwise, quit. After the loop is over, so you're going to go and do the increment step, or the index. And the index will be modified, and then you'll check the loop condition again. So in order, the way that these things go is we have initialization, then we have the loop condition check, then we run the loop. Oops. And then we go back and we increment. And then we go back here. Initialization, check the condition, run the loop, increment, go back up here. Check the condition, run the loop, increment, check the condition, run the loop, increment. This guy only happens once when the loop is first encountered. And these guys occur in this order. Every while loop can be written as a for loop. Every for loop can be written as a while loop. Okay, I'm pretty much out of time. So you can read about for loops. You don't need to use the for loops in this week's program. Those of you that want to hear me talk about the program can stick around for 5 minutes. Those of you that don't want to hear me talk about it can hit the road.
Why?
I like it a lot.
Is it like a combo method?
No, it's
So, Hailstone sequence. Generating the terms. You're obviously going to use a while loop to do this. The real question is, what happens inside the while loop? So I'm not going to write anything out in detail, but I do want to talk about what are some of the steps inside. You start off with, go ahead.
Are you still running the video for YouTube?
Yeah, I am.
So we need to write this down.
Oh, yeah. So I'll keep it running. You start off with some initial value. So in here you've got some initial term, n0. And let me remind you how the Hailstone sequence works, if you don't remember. Oh, my sand pile is getting quite large.
Does it ever hit the block?
Oh, it'll just totally fill up with sand, yes. All right. I can just close that, close that, close that. I'll get out of there, and let's go here. All right, so we've got this initial term. We're going to come in, and to generate the next term, we have to do a test. So let's go, and we test to see if it's even or it's odd. So how is that going to be done inside this while loop? Yeah, exactly. And just before we get there, what should the loop condition be?
Positive.
When does this sequence end?
When it's one. No, it's one.
Something like that? Okay.
We did like n greater than 1, and if you entered something negative, then we had it go back.
And if you want to do that, that's great. But what we care about is if this thing lands on 1, the loop stops. Okay, inside the loop, what happens? So I have to do something for even, something for odd. Somebody was talking about n%2. Yeah, so n%2 equals 0 means even, right? And if it's even, what do? Yeah, and you can do n. How do I overwrite n with half of n? Something like that, right? Okay. If it's odd,
The end of that is 1.
just n equals n over 2. Sorry?
I don't know.
Okay.
It's probably just an else.
Yeah, right. There's only 2 possibilities. It's either odd or even. So this is a perfect situation for an if-else. And if it's else, what's the formula?
n plus 1.
N equals 3n plus 1. And you're just going to keep doing this over and over and over again until the loop condition fails. Until it gets to 1. And the Collat's conjecture tells us that this loop will end. But it is just a conjecture. There's no proof yet that this loop will end. Okay, that's generating the terms. Any questions about that? Let's talk about show terms or not. Lots of different ways to do this. First, we're going to ask the user, do you want to see the terms, right? Presumably, the user's going to provide a response. You have to decide how to store that response. So how do you want to, let's talk about this. How do you want to do this?
A lowercase y or lowercase n.
Yeah, so I could say, do you want to see the terms? And then I could actually provide a little prompt, y/n. You've probably seen this before. It's almost universally recognized as yes/no. So the person hits a y or an n. How do I want to get that data into the program?
Variable.
I need a character variable. So we'll get the response into a character variable. You might want to call it something like response. All right. So now we have the user's preference. How do we implement that inside the code?
Our
have a question. Would you just have two like giant if statements for if they say yes or no?
I would not want to see that
Okay.
for the sake of efficiency. So Sarah's saying Boolean variable. Where are we actually generating these terms? Inside the while loop, right? So we're going to probably want to print them out right near where we're generating them. So here's where I'm generating them. What's a way to do this? What's a way to print them out if the user wants to see them right at the point where they're being generated? I could, but that would always run. If whatever the response is, then cout. Right? So if response equals y, then cout otherwise. So right, sort of sneak it in right here and conditionally print n based on the response. Sorry, you just in that general vicinity. I'll let you figure out where. So my point with that arrow is you want to print these things out as they're being generated, because you don't have any way of saving them all up and printing them out at the end when you're done running the loop, right? Because once you generate the third term, once you move on to the fourth term, the third term is gone forever, right? So you better print it out while you got it. So you ask the user whether they want to see the terms. You get the response into some character variable. I like the yn idea. So I'll put y/n here. And then you put some kind of if statement up here in this vicinity that will print out n based on the response. And I'll let you decide how to implement that. Count terms. One of the things that this thing is supposed to do is say, if I punch in n0 equals 10, or the initial starting point is 10, it's supposed to tell me how many terms it takes to terminate, to get to 1. How am I going to do that?
Could you just put the I++ in twice, once in the if statement and once in the else statement?
Or if I want to run it if and else, just put it in the while loop, right? If it's going to run all the time anyway,
Like at the top of it.
I could just put it anywhere in the while loop. So count terms, initialize a counter. And then increment in the while loop. And then when the while loop's over, or I guess kind of giving it away, when do I show that count? I show the count when the while loop terminates. And this will just automatically keep track of how many times that while loop ran so that you don't have to. Any other questions about this? Is there some major thing that I'm leaving out that you have a question about? Okay, this is due midnight Monday. Start now if you haven't already done so.
Talk about my program.
Sure.